The Air Force had a category for rockets that did not just explode. They turned, kept flying, and threatened places no one expected. Not a fireball on the pad, not debris falling neatly downrange. A rocket still had engines, fuel, guidance, and motion. And if it pointed the wrong way for long enough, the danger moved with it. That is the problem inside a 181-page Research Triangle Institute report issued on September 10, 1996. It was written for the 45th Space Wing Safety Office at Patrick Air Force Base and the 30th Space Wing Safety Office at Vandenberg Air Force Base. The title was dry, Modeling Unlikely Space Booster Failures in Risk Calculations. But the question underneath it was not dry at all. How did the United States Air Force decide which rocket failures it was willing to tolerate above your head? The report's answer begins with a category called Mode 5. Mode 5 meant a failure after pitchover that could send an impact in almost any direction the vehicle still had energy to reach. I used to think range safety meant one basic decision. If a rocket strayed too far, destroy it. That is part of the story. But when I followed this report page by page, the harder problem became visible. The Air Force was not only asking how rockets fail, it was asking what kind of motion a failed rocket makes before anyone can stop it. This is No Secrets. No Secrets follows the documents, the dates, and the gaps. And this episode follows the 1996 risk model for rockets that flew the wrong way. Most of us picture a launch stability as a single dramatic event. A rocket lifts off, something breaks, and the vehicle disappears in flame near the pad or along its intended path. That belief makes sense. The failures we remember are the failures cameras can see. They happen fast, they look final, and they reduce a complex machine to one image. The report itself admits that ordinary failures usually concentrate debris near the flight line. If a booster loses thrust early, it tends to fall short. If it breaks apart under aerodynamic load, the pieces scatter around where the vehicle already was. If guidance fails in an obvious way, range safety may have time to terminate the flight. So the comfortable story says launch risk is mostly a corridor problem. Keep the corridor away from people. Destroy vehicles that leave it. Then calculate casualty risk from debris close to that path. That model is not foolish. It is the reason launch ranges exist where they do. The Eastern Range and Western Range use water, distance, tracking radars, destruct lines, and exclusion zones as layers of protection. For ordinary failures, those layers work because the failed rocket remains close to the expected geometry. But the 1996 report says that is not enough. On page 3, RTI states that risk studies are incomplete unless these unlikely failures are included. That one sentence changes the shape of the whole investigation. Because the danger was not just the failure. The danger was the vehicle response after the failure. That distinction matters. A valve can stick. A guidance command can go wrong. A hydraulic system can lose pressure. An engine can sag below its expected performance. But for people on the ground, the immediate question is simpler. Where does the vehicle go next? That is why the report does something surprising. It does not try to model every possible broken part. It groups catastrophic events into vehicle response modes. 5 are failure responses. 1 is normal flight. That is the first crack in the myth. The Air Force was not only protecting against explosions, it was protecting against bad geometry. To understand why, start with the ranges themselves. Cape Canaveral launches eastward over the Atlantic. Vandenberg launches over the Pacific, often into polar orbits. Both places depend on geography. The ocean is not just scenery. It is a safety system. But geography only works if the rocket behaves like the model summers. The report's authors, James A. Ward, Jr. and Robert M. Montgomery, were working inside that problem. Their customer was not a museum or a history project. It was Air Force launch safety. The report was produced under Air Force Contract F04703-91-C-0112. That contract detail matters because this was not speculation. It was a working document for deciding risk. The program at the center of the report was called DAMP. DAMP was built to calculate launch area risk from vehicle behavior. On page 83, the report explains the key move. It does not model vehicle failures as isolated hardware events. It assumes each catastrophic failure produces one of 5 responses. That is not because hardware does not matter. It matters deeply. But public risk math needs the path of the failed vehicle. A tiny electronics fault and a large engine fault can be different causes. Yet if both make the rocket turn and keep thrusting, they can create the same kind of public hazard. This is where the report becomes cinematic in the least cinematic way possible. It tells us that a technical appendix can be a map of accidents. Every row is a launch. Every anomaly becomes a clue. And every response mode is a way of asking whether the old corridor model missed something. The report's central worry appears early. Less likely malfunctions, it says, may send a vehicle into a sustained turn away from the flight line. Page 11 then turns that worry into a task. The authors had to determine the best values for Mode 5 failure probability and the density function shaping constant, A. That phrase sounds narrow. It is actually the whole fight over how much uncertainty the range must carry. If the probability is too low, the model understates the danger. If the shaping constant is wrong, the risk lands in the wrong place. This is why page 15 matters. The report points to a case where impact would have been well away from the flight line. That is the kind of sentence that makes a safety office stop treating rare as harmless. The hinge is not drama. The hinge is direction. If the turn lasts only a second, the range can handle it. If it lasts long enough, the rocket writes a new map. Mode 5 is the report's most important category. It covers failures after pitchover. Pitchover is when the rocket stops climbing straight up and begins bending toward orbit. Before pitchover, many failures fall close to the launch area. After pitchover, the vehicle has horizontal speed and directional commitment. If something goes wrong there, the path can become stranger. The report says Mode 5 vehicles may impact in any direction from the launch point within their range capability. That is a cold sentence. But imagine what it means operationally. A rocket can be aimed east. The population at risk can be north, south, or even behind the intended path. The people exposed may not be standing near the flight line at all. That is why rarity does not end the discussion. A rare response can dominate risk where ordinary responses contribute almost nothing. This is the second crack in the myth. We tend to rank dangers by how often they happen. Range safety has to rank them by where they happen and who is underneath. The report does not pretend Mode 5 is common. For mature Atlas, Delta, and Titan vehicles through early flight phases, it recommends Mode 5 at 7.9% of failure responses. Mode 4 dominates that same set at 86.2%. That comparison is the trap. If you look only at the percentage table, Mode 5 looks secondary. If you overlay geography, the small number changes character. For new liquid propellant systems, the report recommends a higher Mode 5 share, 15.3%. That difference makes intuitive sense. A mature rocket has more flight history. A new system has more unknowns. But even the mature number is not zero, and in public risk, non-zero matters. The report also gives vehicle failure probabilities for early flight phases. Atlas appears at 0.031. Delta appears at 0.013. Titan appears at 0.064. Those are not destiny numbers. They are inputs for a decision model. The Air Force still had to ask what each failure would do in motion. That is why a smaller Mode 5 slice could not be dismissed. The report then pushes the problem further. Some Mode 5 responses were so convoluted that they resisted simple description. That is not a weakness in the writing. It is the point. A rocket failure is not a billiard ball. It is a powered machine with guidance, structure, aerodynamics, propellant, and sometimes enough control authority to do the wrong thing beautifully. That is the terrible elegance of Mode 5. The vehicle is not dead. It is wrong. And this is where the document changes form. It stops feeling like a model. It starts feeling like an accident archive. Because RTI did not invent Mode 5 in a vacuum. It found the shape in decades of launches, and the archive shows why a wrong-way rocket could not remain an edge node. The appendix begins like a ledger. Atlas, Delta, Titan, Thor. Hundreds of launches from the Cold War into August 1996. The point was not nostalgia. The point was evidence. On January 25, 1957, Thor 101 rose only about 9 inches before falling back on the pad after a fuel system valve problem. That kind of failure is terrifying, but geographically contained. On June 11, 1957, Atlas 4A lost booster performance and was destroyed by the safety officer. Again, the response fits the older mental model. But then the archive starts bending away from that simplicity. On May 13, 1960, the first Delta launch, Echo 1, lost attitude control during the second stage coast period. This matters because Delta was not born as a clean civilian symbol. It grew out of missile-era hardware adapted for space launch. That lineage is why the report can use Cold War missile data without pretending every launch was identical. The authors are not saying the past repeats mechanically. They are saying the past contains response shapes the future cannot ignore. In RTI's appendix, Atlas 8E becomes an off-nominal case with an impact far from the intended line. Public launch summaries describe an early control loss and breakup sequence, so the safest reading is to treat the exact timing as the report's classification, not as a settled public launch history. But the geography is the part RTI could not ignore. It lists an impact 1,316 miles downrange and 215 miles cross-range. That is not a pad explosion. That is a vehicle carrying the consequences of its failure across a continent-scale distance. On October 6, 1961, Titan M4 suffered a 1-bit W-velocity accumulation error. 1 bit. The result was an impact 86 miles short and 14 miles right of target. This is the kind of detail that makes the archive feel human, not because it is sentimental, because it shows how small faults become geography. On July 22, 1962, Atlas 145D carried Mariner R1. Erroneous guidance commands produced a gross trajectory deviation, and the vehicle was destroyed. This is the Mariner 1 failure in the broader launch safety memory. It reminds us that software and guidance are not abstract. They point metal, fuel, and flame. Then comes Delta. On September 18, 1968, Delta Intelsat III went through violent pitch and yaw maneuvers. It briefly regained control, then quasi-control was lost, and the vehicle broke up. That phrase, quasi-control, is chilling because it sits between safe and gone. A rocket can be neither healthy nor destroyed. It can be wrong for long enough to matter. On August 27, 1969, Delta Pioneer E lost first-stage hydraulics. It tumbled. Then its second stage regained control in an abnormal attitude before destruction. That is Mode 5 logic in miniature. The failure did not simply end the flight, it changed what the flight was. On December 8, 1980 local time, Atlas 68E lifted off from Vandenberg on the NOS-4 or Parse-4 mission. Public launch histories describe a B-1 booster engine shutdown shortly before booster jettison, linked to turbopump lubricant or plumbing trouble. The vehicle then flipped roughly 180 degrees, looped back, and broke up or was destroyed by range safety. That is the image that stayed with me. Not chaos. A launch vehicle turning its energy back against the map it was supposed to leave behind. By June 1991, the Joust, also called Prospector failure, gave the Eastern Range another example. After aft skirt structural failure, the vehicle performed a radical pitch up. The report treated the resulting impact trace as Mode 5 evidence. 2 months later, on August 20, 1991,
a guided Red Tigris sounding rocket cleared its launcher and turned nearly 90 degrees. It then flew stably in that wrong attitude until destruct. On page 143, the report describes a vehicle that remained in stable flight in that attitude for about 240 seconds before the safety officer destroyed it. That does not mean 4 full minutes of motor burn. It means the range was watching a wrong-way vehicle remain coherent long enough for time itself to become part of the hazard. By now, the misconception is gone. The archive shows explosions. It also shows turns, tumbles, recoveries, abnormal attitudes, and stable, wrong-way flight. That is why Mode 5 exists. It is not a theory looking for accidents. It is accidents forcing a theory to exist. The next question is harder. How do you assign numbers to something rare? RTI considered reliability methods based on parts and subsystems. On paper, that sounds objective. Count the components. Estimate the chance each one fails. Combine the results into a vehicle failure probability. But on page 22, the report says both major approaches have serious problems. Complex launch systems are too interconnected for clean certainty. A part can fail without killing the mission. A small fault can cascade through the whole vehicle. And expert judgment can quietly become subjective. So RTI leans toward flight history. On page 24, the report calls statistical analysis the only completely objective way to estimate vehicle failure probability. But even that is not simple. Rockets change. Factories change. Procedures change. A launch in 1957 does not carry the same meaning as a launch in 1996. That is why the report describes filtering and data weighting. Recent flights receive more relevance. Representative configurations matter more than obsolete ones. But the sample gets smaller when you filter, and rare failures almost disappear. Page 33 acknowledges that problem directly. Because representative samples had too few failures, the report estimated relative mode probabilities using all vehicle configurations. That is the methodological compromise. Use enough history to see rare response modes, but weight the data so obsolete risk does not dominate modern decisions. Then comes the hardest part. Mode 5 is not just a probability. It also needs a shape. If a wrong-way rocket can go many directions, how should risk fade with distance and angle? The report used shaping constants called A and B. A strongly controlled the launch area risk estimates. B mattered less when A was chosen appropriately. But page 40 says adequate test data did not exist to establish the Mode 5 shaping constants empirically. So RTI had to simulate. Monte Carlo simulation is not a magic phrase. It means running many randomized versions of a problem to see the pattern that emerges. For Mode 5, the report simulated random attitude and slow turn failures. It tested how far vehicles might deviate before breakup. Breakup strength mattered enormously. The report expresses that strength through dynamic pressure times angle of attack. In plain terms, a fragile vehicle breaks before it can wander far. A tougher vehicle can stay intact while flying deeper into the wrong map. That is a frighteningly practical insight. Strength can improve mission reliability. But in a wrong-way powered failure, strength can also extend the danger. This is where the report earns its weight. It does not pretend certainty exists where data are sparse. It builds a model anyway, because the range still has to decide. Launch or no launch. Accept the risk or change the plan. The math is not abstract. It is bureaucracy trying to put a number on fear. So what did the Air Force really learn? Not that rockets fail often. Not that every launch threatens every town. Not that range safety was careless. The lesson was sharper. The failures least likely to happen could shape the risk most strongly for people farthest from the flight line. That is the aha inside the report. Mode 5 was not a footnote. It was the category that forced range safety to admit the map could rotate. Suddenly, the odd histories make sense. Atlas 8E explains cross-range reach. Delta Pioneer E explains abnormal recovery. Atlas 68E explains loopback danger after a propulsion failure.
Red Tigris explains how long a guided rocket can remain coherent after turning the wrong way. And the Monte Carlo work explains why the report could not wait for perfect data. If you wait until a rare failure gives you a large statistical sample, the sample may be written in casualties. That is why the model matters. It transformed frightening anecdotes into categories. It transformed categories into probabilities. It transformed probabilities into maps. And those maps shaped whether a launch was acceptable. This is not a story about exotic weapons. It is a story about official assumptions. The dangerous part of a risk model is often not what it hides. It is what everyone quietly agrees to treat as normal. Looking back, the 1996 RTI report is not dry at all. It is a map of how Cold War rockets taught post-Cold War range safety to fear the edge cases. It shows that public safety depends on the failures engineers least want to imagine. And it shows that a small percentage can matter if it points toward people. This report reminds us that safety is not just preventing disaster. It is naming the disaster before it has a clean name. But the report's authors left one question unanswered. Which parts, if any, of this Cold War-derived modeling logic survived into later launch safety rules? No. Secrets follows the documents, the dates, and the gaps. If assumptions from this Cold War-derived risk model survived into later range safety practice, the public deserves to understand the math. Watch the next No Secrets investigation. Which assumption in the USAF 1996 RTI report would you audit first? The unlikely Mode 5 percentage, shaping constant A? Or the space booster breakup limit? Follow the records.